We had. D is not. Oh yeah, it is. D squared plus 2. I don't know. It's so if you did it normally, it'd be 1 would be plus I, 1 would be minus I.
Oh, okay. So you're saying that this is really the same as D plus 2 minus I.
And then D.
Right. So we can factor, and then you can just square the factorization. You get the squared.
Yeah.
So right. So this should give us like Z e to the minus 2 plus I t, and also z2 e to the, well not, but it's repeated, right? So we get t e to the minus 2 plus I t, right?
Yes.
And likewise, we get z1 conjugate and we get z2 conjugate over here.
Let me catch up for a second.
You're good.
Oh, my biology was so easy. I write my notes before class. I can just pay attention. Come back to this. Squared plus 4D. Squared. You can go.
So z1 is e to the minus 2t cosine t plus I e to the minus 2t sine t, right?
Mm-hmm.
And z2 is really just t times z1 if you look at it, right?
Well, where did you get the Z1 bar and Z2 bar from?
It's a complex conjugate, like it's just
Oh.
the same with
The
I
minus.
replaced minus I.
Okay.
So those aren't really, my point to you is that from z1 we get the real part and the imaginary part.
Yep.
And from z2 we get also another real part and imaginary part. Remember what we're aiming for here. We're aiming for how many real solutions? Well, what's the order of our original order? 4, right? So we're done.
Yeah, we have 4.
You know, y is equal to c1 e to the minus 2t cosine t plus c2 e to the minus 2t sine t plus c3 e to the minus 2t t cosine t plus c4 e to the minus 2t t sine t. You can put t before or after whatever.
Yeah.
There you go. And you can see that from just picking off the real and imaginary parts of the e to the lambda t to the lambda t complex solution. So really, if you carefully prove the claim that the repeated case has, exponential t times exponential all the way out to t minus 1 times exponential, then you can use the complexification theorem to pick these out. And that's how we. So that's everything, because if you look at the nth order problem, you either got repeated linear factor, in which case you get exponentials and t times exponentials, powers of t times exponentials, or you have a repeated prime factor, which gives you sines, cosines, or exponentials times sines and cosines, or t times exponentials and sines and cosines.
So if we have a different algebra, I'm gonna make this hopefully nice and say it's isomorphic to anything cross C, and we have repeated root, and we have an equation of the C part.
Ooh, yeah, I don't know.
Could we? Because
I don't know about how. I don't know how to connect another algebra to C necessarily. Like, I'm not sure that there's an imaginary unit in other algebras. I can adjoin one. I can take the algebra and I can extend it to a bigger algebra which has an imaginary unit. I can complexify the algebra
Yeah.
to join an I. Whether or not there's an I there already to start with, I don't know.
Well, if we, if we can complexify it, that means we should be able to solve in some cases some hard differential equation that's not factored,
Yes.
which is good.
Mhm.
But what I was saying is I don't know what I'm saying now.
Okay.
Because we have like C cross R, and so we'd have a real function and a complex function,
Yeah.
and how would that work out? Anyway,
So that
could you complexify one part of it?
I don't.
You know, like if we have a real complex number, we can complexify the real function
Oh,
and then bring it back.
I don't know. Like when we get to that stupid solution I'm talking about,
Yeah.
we just we create the algebra that works for us
Oh.
and work there pretty much. Should I clean up the table, Jimmy? What's that? Yeah. Okay.
Whenever they were asked